We're going to develop a model predictive controller for this dual tank gravity drain system. What we have here is a first tank with the liquid that drains down into the second tank just because there's a hole or an opening in the bottom of that, and it drains into the second tank, which fills up, and then that also drains down into a larger reservoir, which then is pumped back up, and we can control the pump. So this is our manipulated variable, and the thing that we're going to try to control is a level on tank 2. So tank 1 is not going to be measured, just tank 2, and we're going to try to control this with model predictive control. So in looking at this, we're going to just do a couple different things. We're going to first of all come up with a model of our system, and then we'll develop a suitable approximation to that system. Let's say perhaps we want to do linear model predictive control. So we're going to derive a linear model from the nonlinear one that we derived before. Okay, and then we'll implement the model predictive controller and then tune the application. So first of all, the modeling of this. We know that with Bernoulli's equation that the outflow is going to be dependent on the square root of the height in the tanks. And so if we just do a mass balance, change in mass in that tank of liquid is going to be equal to the mass flow rate in minus the mass flow rate out. So we have accumulation equals in minus out. You would normally have generation and then minus consumption, but with mass we don't typically have those unless it's a nuclear application. So then we take this, and mass is going to be equal to density times volume, and we also have density. If we do volume equals the area times the height, then we can plug that in right there. If the density and the area are constant, then that leaves us with density, area, d height, d time, and then the mass flow rate in, we're just going to say that's going to be a constant, one constant times the pump rate. It's going to be proportional to the pump rate, and then the mass flow rate out might be another constant times the square root of the height. So we're going to use this to develop a simulation of this. So let's just go to MATLAB. You can download all these files that I'm showing if you just come to this web address here, and this will have some of the starting files in Simulink and Python to do some step tests and be able to observe how this model is performing. One other thing I failed to mention on this modeling is that this would just be, for example, for height 1, and then we would have another one for height 2 as well. Very similar form. Okay, and we also have a valve here that can direct the flow either to tank 2 or tank 1. So we have a valve position here, and so I'll just say that is going to be 1 minus V right there, and then what comes in to the second one might be equal to V. So if V is equal to 1, then it's going to be coming into the second one, and if it's equal to 0, it's going to be going into the first one. And then we also have a loss term. Let's say we have the same coefficient there. It might be a different size opening. Let's just assume that they're the same for now. And then you also have what's coming in from the tank up above. Okay, so this would be the form of the two differential equations, and we'll just simulate these just with some default parameters. If you'd like to get those parameters, you can see those from the model. Okay, so I'm going to run this. This is just a Simulink model. We'll go ahead and simulate it with a couple different pump outputs. Okay, so here is the tank filling and draining, And I'll just go ahead and slide this back and forth. The pump, so if I increase it, it's going to fill up tank 1. If I decrease it, tank 1 will go down, but tank 2 is still increases for a little bit because of all that flow into the second one. And we're going to try to make that get to the red bar there, meet the red bar target. And so I'm going to be adjusting this pump to be able to get to the red bar set point on the second one. Okay, so this would be manual control, or also for generating data in order to be able to come up with this surrogate model. And you can see it running here, just steps up and down. As we do step tests, we'll get better data for our surrogate model. Okay, and then I'll go ahead and turn this off. Okay, so you can see the dynamics there of how the tank fills or drains with those two coupled differential equations. Okay, so it finished. Here's the performance that we had. Here's the pump out going up and down as I adjusted it. Okay, and there you can see the level 1 in the third subplot, and then the level 2 and how I did in terms of trying to meet my set point. The valve position was equal to 0 the whole time, so it was all directed into the first tank, the one up above. Okay, I'm going to go ahead and close this one. And again, those files are available for you if you'd like to download those. Okay, so we have these. We came up with our nonlinear model and we tested it with some step tests. And now we want to do an approximation, a linear approximation to that nonlinear model. So you can either linearize those equations, that would be one approach, or you can try to fit a first order, second order process model to that data. So I've already done that. Here's a couple equations, but if you wanted to formulate something like two first order systems, and there I have four unknown parameters. Okay, I want to minimize the difference between the measured height 2 and the predicted height. And there's more information on how to do this on the course website under the estimation. Okay, so for example, if you just go to introduction, you'll see how to formulate these problems. You can do it with Excel or with MATLAB or Python. Okay, we're not going to get into that in a lot of detail because I want to spend most of the time on the model predictive control. So after we have this suitable approximation to our system, now what we want to do is use that in a model predictive controller. Okay, we have the parameters that we may have obtained from the estimation, and there you can see the parameter values that we're going to use. Okay, I'm going to go over to Python now, and this is going to be Gecko Python. And as we start going through this, I'll just go ahead and relate that to what we've already done and kind of sketch out what we're doing. We're going to just import some packages first. Okay, and I'll just save that as level.py. We're going to get numpy, matplotlib for plotting, and then also scipy. We're going to use scipy integrate, the ODE int, to be able to integrate our nonlinear model. And then we'll do the linear model predictive control in Gecko. Okay, so let's go through this. We're going to create a new Gecko model. So this was our second one. We got our linear approximation, and now we're doing the model predictive control. We have our time horizon there, the time points that we want to go off into the future. So we have 1, 2, 4, 8, 12, 16, and 20. So we're going to be making approximations to the pump in that future horizon to try to drive us to a target set point. There are constants that we just got. Okay, the empirical constants that we identified from this model right here. We're going to put in this model we have the pump. Okay, so just as this is going, let me go ahead and just talk about that. The pump, we're going to have its status on, meaning that it becomes a manipulated variable that we can adjust. We have its lower and upper bound. I just put the lower bound as 1 times 10 to the minus 5th because it doesn't like in the square root, if you have a level that's equal to 0 or less than 0, it kind of gets the ODEint kind of messes up. So we have a decost, that's the penalty on moving that parameter. So if you have a lot of movement on the pump, it helps to suppress that movement. Okay, the F status means I'm not measuring it, no feedback status. And then H1 is this variable right here, my linear model, initially equal to 0, and H2 is this variable. Okay, I also have a trajectory initialization. That's going to be a reference trajectory. I have my first equation there, and the derivative, you just do h1 dot dt like that. Okay, and don't forget the double equal sign in Python Gecko. You just have to replace that with a double equal instead of a single equal sign. And then imode equals 6. That is going to be the control mode, the model predictive control mode for Gecko. And then CV type, that means that we're following a squared error objective. So here is my set point, and the tau value says how fast I want to get there. And so that's going to be my target as I try to drive to that new set point. Here's my tank simulation. So as I go up, this is the simulation of the nonlinear model. And I just put in clipping there of 1 times 10 to the minus 10th just for the level so it doesn't go below 0. Seems to have some numerical problems in ODEint if you let it go to 0. I have the inlet valve coefficient, C1, and then also a tank outlet coefficient. That's the draining part of it. It's going to be multiplied by the square root of the height. So here's my first derivative. So I'm coding this up twice. You'll notice that we have, right here we have our Gecko model. That's the linear approximation, and then this one is going to be the nonlinear one. So what we're doing is we're setting it up so that every cycle we are taking a measurement. Okay, we're taking a measurement and then sending that to the controller. So this is going to be the model predictive controller. And the model that we're working on right now is the simulation of this system. So those two can be different. You don't have to use the same model for the model predictive controller as the one that represents reality. Okay, these are the overflow conditions right here. If h1 is greater than 1 and I have a derivative that says it wants to go further, just set the derivative value equal to 0. So that means if I get all the way to the top, I spill over the top. So overfill conditions, and then we need to return our derivative vector. Okay, derivative list there of the two derivatives. And I'll just return that, and then we're going to use that in the ODEint call to be able to simulate our system with different pumps. Okay, our initial conditions are 0 and 0 for both of those tanks. So they start off at completely empty, and then they're going to fill up. I'm going to have 400 seconds this is going to go through. So just as it's going through the rest of this, I'm going to bring up, let me just bring up the, okay, I'm going to go to desktop, and I'm going to run this one that's already there. So just as it's going, we can talk about it as it's going through this simulation, and we'll bring up the plot here off to the side. Okay, so we'll have different set points that we're going to go to, and you can see the black line, that is a set point for the height 2, and you can see the time that's elapsed there. The pump is down at the bottom, so that one is went to 1 or all the way. And we're just setting some initial values there in the script first of all, and then we're going to just put in some things to be able to record the solution so we can plot it. Okay, so we're trying to drive the red line there in the top subplot to the set point. And right now we're just putting in some, putting in some things to be able to do the plot and create a real-time plot as you see it working there in Python. Okay, so it's simulating like a real system, as if we're going through this sequentially and getting measurements sequentially. There you can see a set point change. You can see on line 66 the set point changed at cycle 100 after 100 seconds to 0.8, and so you can see it trying to track that new set point. Okay, now we enter in the script, we're entering our main loop here, and this is our MPC controller that we're going to be that we're testing here, as you can see in the plot. Okay, and so we have, first of all, we insert the measurements into the MPC. We say that the measurement is in the second tank, so you use y I comma 1 instead of y I comma 0 would be the first tank. Then we have to do our set points. Okay, we have our set point high and set point low. I'm also going to put in just the set point. In this case, we are using the squared error, so a single reference trajectory. So we're also going to put in the set point. But if you changed, up above, if you changed the, the CV type to 2 or to 1, then we'd use a set point high and set point low. But in this case, we're just using a single set point. Okay, we're going to solve the MPC. We issue the solve command. And then if you put disp equals false, then it doesn't display the solver. If you put remote equals true, then that sends it to a remote server. That's true by default. You can set it to false if you want to solve it locally without an internet connection. Okay, there you can see the set point dropping here on the right. We have the pump new value that's being returned from the MPC, and then that's going to be injected back into our system for another cycle of simulation. You can see we're going from I in range 1 to time final, and so we're just stepping through these 400 time seconds, simulated seconds, to be able to simulate how well we're tracking the set point. So every second we're giving new data to the controller, and the controller is trying to decide what to do with its imperfect model to be able to project into the future. Okay, here we simulate the ODE with ODE int and our inputs. We have our pump and our valve. Although the valve value is just set to 0, you could change that if you want to change that between 0 and 1 and direct more into the second tank. Okay, we're going to record the result, and then we'll reset the initial conditions as well, the height 0, for our next cycle. So every time you go through this loop, you're just simulating 1 second and then letting the model predictive controller come up with a new pump value. Okay, then we're going to update our plot. We'll just do it every 5 cycles, so sometimes this slows the simulation down. So I just said mod 5 on the I iterator. If that's equal to 3, then you clear the figure, and then we'll plot the rest of the results. Okay, so here's our model predictive controller. We're using a second order linear model to be able to control this height 2. You can see that the pump has fairly good, it's responding fairly aggressively. One thing that I don't like about this though is that we're overfilling tank 1. So you can see that in the blue trend there. I mean, that's just for information purposes on the height 1 and height 2. So we may want to avoid that. We want to avoid, overfilling tank 1. One of the ways to do that is to try to model better the tank 1 and then put a constraint there. The other way is just to make the controller a little less aggressive, so it doesn't try to fill up tank 1 really fast in order to get faster response on tank 2. Okay, so it's almost done with this simulation. I'm just going to change one thing about this, which is going to be my reference trajectory, how fast I want it to get to the new set point. And we'll see if that helps, and we'll run it just one more time. Okay, so after it reaches the 400 seconds, we'll go ahead and stop it and then try it again. Okay, there you can see my plots. I'm just doing my subplots, and okay, so this is all done. You can see the performance fairly good, but we overfilled tank 1. So let's go ahead and do the tuning. So this is the third part of developing a controller. Okay, we had MPC control right here, and now we want to tune it. So let's go in and see if we can tune this application. You know, there may be some undesirable things that are there. So let's just go in and see if we can change the value and get a little bit better performance here. Let's slow it down a bit. I'm going to go to maybe 35 on that time constant, and I'll talk just a little bit about why we changed that. Okay, and let me open this back up as well. Okay, so the time constant for this, and you can see, I'll just leave this plot open as it's going. We'll see if it doesn't overfill as much, or okay, still a little bit too fast there. Let me go ahead and kill that. Execution, and go ahead and just do Control C to stop it. And so let's set that more like to something like 50. Okay, and let's see if we can slow it down a little further. Okay, so we're going to slow this down. Let me just share the equation that we have. It's going to be the time constant is going to be equal to the amount of time that it takes to get 63% of the way there. Okay, again, this is just a little bit too fast. I'm going to try some other things here. Okay, it's still overfilling in tank 1. So let's just see the, sometimes with these real-time plots it's a little hard to close the plot. It'll try to reopen it again. Okay, so sometimes you can do things like trajectory initialization too. I'll talk about some of these options right here on tuning the CV values. And so if I run it one more time, okay, the time constant is going to be amount of time it takes to get about 63% of the way to the new set point. And so if we think about that, we're going to ask for a new set point, okay, maybe to 0.5, and that's the amount of time that we're going to say is to get 63% of the way there. The way that we write this out is we have the trajectory. It's actually a little differential equation plus a set point. And what we're doing is we're just getting to define this first order reference trajectory with this adjustable parameter tau. Now the analytic solution to that, if you solve that out, you have that the trajectory as a function of time is going to be 1 minus e to the minus t over tau. Okay, then times the change in set point. And so this, if you plug in time equals tau, you get 1 minus e to the minus 1, and that equals 0.63. That's one time constant. So that's about how long it takes to get 63% of the way there. Now if you use trnit, that was another parameter. trnit, when it equals 0, it's just a pure deadband. So if you have a set point, or a set point high and a set point low, then it's just going to start at those values initially and try to drive that into that region as fast as it can. Now if you use option 1, what that does is it starts here, and then it draws your trajectories up to your new set point high and set point low. Okay, and tells you to go at that time constant, tau. That's how long it takes to get about halfway there, a little over halfway there, 63% of the way there. Okay, and that the difference between 1 and 2 is that 1 tells you to get there and does not reinitialize that value. So let's say you went up a little bit like that, it would tell you to come back down, okay, into that trajectory, whereas option 2 would do that same thing, but it would redraw up to the set point high and set point low. It would recenter your trajectory in that region. So this was your old one, let's say, and it would readjust itself to your new value, okay, if there's a little bit of mismatch. Okay, so now you can see that we're not overflowing height 1. It's a lot less aggressive. We're also not really making it up to the set point as fast. Okay, so that concludes this tutorial on model predictive control. We've done 4 things. We developed the model and did some step tests. We developed a surrogate model in a very high level, not in a lot of detail on those two. But then we developed the model predictive controller with Gecko, and then are simulating the model predictive controller with the original nonlinear equations. And then the final step, we tune the application to try to do some better response on the controlled variables.